So we were talking at the end last time about this model called the EVW model. And it's just another way to formulate and write out your logistic regression models in a way that sort of parses the variables into the pieces that we care about as epidemiologists. So the exposures, potential confounders, and the potential effect modifiers, right? So the E's are exposures, the V's are the terms that contain confounders. And we said, we had this really complicated looking sort of model here. We said that you can have C variables, sort of control variables, and sort of different things, special versions of them, so a C squared and a sex times PAMU. And these all sort of operate as confounders. These are all just extra things to control for in the model. But they're not effect modifiers because they're not multiplying the exposure. And so these are terms that if you have age square in the model and you're interested in the odds ratio for exposure, this is going to control, you're controlling for this in order to get a better estimate of the exposure odds ratio. But that's sort of what, that's why these are V terms. They sort of sit by themselves. And then we have these other terms that are multiplying by exposure, and these sort of operate in an effect modifying sort of way, age, sex, PMU, and then sex by PAMU. And then we essentially rewrote this model above in terms of the E's, the V's, and the W's. We even gave them their own coefficients. So beta is sort of reserved now just for the exposure. And then you have gammas and deltas sort of corresponding to the V and the W terms. Okay, so that was sort of where we landed at the end of last time. Okay, so I said to bear with me because this actually lends towards a simplification of things. And we already talked about these, or just the definitions of those variables. And so what happens is when you can essentially now write your logistic model as 1 over 1 plus e to the minus alpha plus beta times exposure plus the sum of all the gamma times V terms plus the sum of all the delta times the EW terms. This is just, instead of just having lots and lots of betas here, we're just now saying, okay, if you have 6 V terms, this is a way to represent the sum of the 6 V terms, and if you had 10 EW terms or whatever it is, this is just a shorthand for putting them all over here. Okay, so basically the model has sort of 3 units to it: exposure, confounders, effect modifiers, not just like a whole smattering of beta times x's. There's sort of we're sort of putting them in 3 different buckets. And so that's actually a rather convenient thing to do. And this is the probability sort of version of the model, the risk version of the model on top, and then the bottom is our familiar logit form of the model. And again, it's sort of, you have these 3 pieces: alpha plus beta times exposure, sum of the gammas times the V's, and the sum of the deltas times the EWs. Okay. So one piece here to notice, there's a little difference between these 2 formulas. And on the bottom one here, notice here's the exposure term. Exposure is multiplying, if you have the sum of a term where you have the same exposure variable, exposure is just sort of a constant in here every time. The W and the delta are changing from 1 to however many terms, 1 to 10 interaction terms or whatever it is. You can factor out the E, because it's just a constant. It's the same exposure variable for everyone. Given you have this one person, one observation of data on somebody, it's the same. They all have the same value of exposure. So you can factor it out, and it becomes E times the sum of the deltas times W. This is actually handy because, as you'll see when we compute the odds ratio, it's nice to have this E factored out. Okay, so. But this is just sort of an algebraic trick. Like the sum of a constant many times is the same as the constant times the sum. This is just factoring out something from a summation. So this is an equivalent, mathematically equivalent to this version up above here. Okay, so this is again just a regular old logistic regression model, but just with some substitutions for these various pieces that we care about. Okay. So what happens is, knowing what we know about the formulas for odds ratios, this is actually the odds ratio formula this is the, this is when we had sort of some general versions of the odds ratio formula, and we had one where there was a single exposure with interaction. That's what this was that formula over here. And what happened, we noticed this pattern when we had worked through this a few lectures ago, was that when you had effect modifier terms, those stayed in the odds ratio expression, and all those main effects for the confounders sort of went away. And the way we can sort of write that now is that the odds ratio for the exposure is e to the beta plus the sum of the deltas times the W terms. So this is the effect modifier terms over here. So this is the expression for the odds ratio, just sort of was what we saw before when we had effect modification, and now we're just substituting in the deltas times the W's. So here we go. So if we had this model 2 that we saw before earlier, this was a model that had age, sex, and PAMU along with E for previous hospitalization. And this model had control for age, sex, and PAMU as confounder terms or V variables. It also had them as potentially effect modifiers. So this EW1 term means the effect modification term for age and exposure. So this would represent the exposure changing across levels of age, across sex, and across PAMU. So this was one sort of model that we considered before. The expression to get the odds ratio essentially is this: e to the beta plus delta 1 times W1, delta 2 times W2, and delta 3 times W3. So the deal is all these V terms go away. And so what's nice about if you label your variables by what are the E's, what are the V's, and what are the W's, you can quickly sort of get to that odds ratio expression by crossing out the V's, essentially. Because those are the terms that we know will go away, because they're going to have the same value in the sort of that numerator and denominator of the odds ratio expression. Okay, so e to the beta, and then you keep the W terms essentially here in the odds ratio expression. So this sort of lets you quickly identify the form of your odds ratio. So this is essentially intuition that we saw before, but sort of labeling the variables this way helps you more readily do that. Okay, so the deal is, right, so all the gamma terms go away in the expression for the odds ratio. Okay, that's sort of the key piece here. And what's nice here, again, I've said it several different ways, is that this EVW model lets you parse the logistic model into things we care about as epidemiologists. The main sort of effect, the confounders, and the effect modifiers. And so you can, especially when we get into modeling strategy, you can find yourself in a situation where you have 5 or 6 confounders and maybe 20, when you think about all the ways that you can make interaction terms and effect modifier terms, might have 20 effect modifier variables, and the bookkeeping can get sort of nuts. And so doing it this way lets you sort of reduce the complexity of your model and say, okay, these things will not appear in the odds ratio. We're not going to, when we set up our odds ratio or our contrast statements to get the odds ratio at a SAS, we're going to ignore the V terms. So again, this is a tool. This is not, this is sort of our tool for navigating logistic models through an epidemiologist's lens. And so I'll just sort of carry through in this next piece, sort of revisits things we did previously about statistical inference, the hypothesis testing, and confidence intervals on the general logistic model, but how this looks when you express things as the EVW model, right? So, for example, this is our model. This was model 1 that we had before in the MRSA data. This is the no interaction model. It has exposure and 3 V terms for confounders. And again, the 3 things we sort of want to know are what's the odds ratio, is it significant, and what's the confidence interval around it. These are sort of the key 3 things we want to know generally from our logistic models. We're going to talk in a few weeks about other things we want to know from a logistic model, like ROC curves and prevalence ratios and some the sort of more newer age things. But these are sort of form the core 3 things people generally first want to know about a logistic model. And so we know that this one is easy, e to the beta, right? We know that already. we wanted to be able to do the significance test of whether that e to the beta or the odds ratio is equal to 1. And that, as we talked about last time, was the likelihood ratio test or the walled test. And then this is the form for a walled confidence interval around the odds ratio. Okay, this is all stuff we said last time. Okay, so again, this is just revisiting ideas, but now it's all expressed as an EVW model. And this was the odds. So that this is our model, our beta times exposure. That's our 3 V terms here. Again, this is output that we've seen before. And there we go. So here, notice this first table. This is when we talked last time about the likelihood ratio test. We didn't actually have any screenshots of where you get that out of SAS. So the likelihood, remember I said you don't exactly get the likelihood directly out of SAS. You get the -2 times the log likelihood. That's the third row of this table that you get first, called the model fit statistics table. And which of these two do you want? You want the one on the right, intercept and covariates. And this is the piece that tells you the -2 log likelihood of the model that you have at hand. Remember we talked about the -2, the likelihood ratio test as sort of a comparison between two models, the one that has the variables in question and the ones that drop the model that versus the model that drops the variables. And so what you do is you essentially run this twice. You run your model twice, and you go look at this table twice, and the difference between these two pieces is what you use for your likelihood ratio test. So here's other key pieces. This is our beta hat. Okay, this is the standard error of beta hat. This is the walled test that we've spoken about. And here's the confidence interval produced for you nicely in this odds ratio table. And we said that this odds ratio table is only valid really in the no interaction sense. This is just a table of e to the betas. It's also not valid if you want to do some other things. If you took a look at that extra slide set on odds ratios, which I know you all ran home and did after Tuesday, if you have looked at it already, which I encourage, we had a piece in there about what do you do about odds ratios when you have continuous variables. Like age in this model is continuous. Okay, so in this model, age is continuous in 1 year increments. And so what does the odds ratio here represent if it's continuous with 1 year increments? It is the odds ratio for a 1 year increase in age. And so this literally means that for every year older you are, your odds of the outcome is increasing by 0.036. So very small changes in the odds, but over 10 years or over 20 years, that sort of accumulates. And so what you essentially have to do, and that slide set shows you that what the odds ratio for a 10-year increase becomes e to the 10 times beta. And so this table is not the odds ratio if you care about a 10-year increase. This is just a 1 year increase. This is sort of a dumb table for many things. So if you want a 10-year increase and its confidence interval, this is not the table for you. Okay? And if you want to know how to do that, there's sort of two ways to do that. One is going to be the contrast or estimate statement, which is coming up in a few slides. You hopefully have seen it already through lab. And then the other way is there's actually a statement called units in proc logistic where you can say, hey, I want this table with units of 10 years, not 1 year. So you actually can tell it for a continuous variable to just adjust the table. But the sort of the most powerful way is going to be with the contrast and estimate statements, where you basically get SAS to do whatever you want. The downside or the hazard to that is that if you tell it the wrong thing, it will give you the wrong thing, and it won't tell you, hey, I'm giving you the wrong thing. You're just going to get the wrong answer. So so that's where you as the artful user come in. So here is just, this is with our model 1, the likelihood ratio test, just sort of illustrated. And this is showing the full model and then the reduced model run down here. And so here, these two pieces, this is the -2 log likelihood for the full model and then the reduced model. And here we're carrying out the likelihood ratio test for whether exposure is significant. So this is sort of a weird model. Look at the reduced model. It's a model that has the confounder terms but no exposure. This is actually a model you're never really interested in life. It's just a model, right? You're fitting a model with no exposure. It's just got the other stuff. And so it's only being run for this comparison of does the likelihood significantly change when we drop the thing we care about, which is the exposure. And so you do this, you run it twice, you get 279, 295, and then this difference has a value of 16, which on a chi-square distribution of 1 degree of freedom, because it's dropping one term, that's highly significant, that's way out in the right tail, and you're going to say, hey, that's sort of unlikely, and it's because it's unlikely, it's got a low p-value, right? That's sort of the whole idea with hypothesis testing, right? Tiny, tiny chance of being observed by chance. Anyway, so that's the likelihood ratio test. And by the way, here, notice, why did I circle this? What's this? It's this, walled. It's the wall test. So this sort of dovetails with something we said last time, is that the wall test gives you a bigger p-value than the likelihood ratio test. This is 0.00006, right? And so that's a tinier number than 0.002. So this qualitatively, you're going to make the same call. You're going to say, hey, looks like exposure is highly significant. But you can imagine that if you had less data or a sort of a more marginally important association, that you might find yourself split where maybe per the wall test, you have a non-significant value, and per the likelihood ratio test, you do. So this is where I was saying that the likelihood ratio is a slightly more powerful test. This is more annoying to do because we had to run two models. So in life and in practice, choose what works best for you, but this sort of just illustrates that distinction. So it's just it's the way it is. So here's model 2. We're going to do something else with this model 2. This was a model that had some nice complexity to it here. It had this had exposure. It had 3 V terms, the 3 confounder terms here, H, sex, and PMU, and then the all-star again as 3 effect modifier terms, EWs. And here I'm writing it again. I'm just writing this as a shorthand with summation signs. This is the same model again. Okay, so here's what this looks like. In fact, if I gave you this table, you'd be able to write this model pretty quickly because it says priv hosp times age. These just scream EW terms because they all have, at least to me they do, and these are because these are all the exposure here. So this is what you would get out of SAS when you fit this model. And this is knowing what we know about our new way of writing the odds ratio formula. If I said, how do I get exposure odds ratios out of this cuckoo model? Well, you would just cross out all the V terms, and then you say e to the beta plus all of these all the W terms. Sorry, all the delta times W terms is the expression for the exposure odds ratio. So basically, you can just take our SAS output, plug it into our formula, and this is the exposure odds ratio formula. Okay, so it's got a lot going on, right? It's got age, sex, and PAMU because, as we said before, the whole point of effect modification is that the effect is changing across values of other variables. And so there is no one odds ratio anymore, right? It's a function of, well, okay, what's the sex of the individual? Have they had previous antimicrobial use? You need to know other information to determine the exposure odds ratio. Okay, it's not just e to the beta, it's got all this other stuff going on. Okay, so the nice part is we had a sort of a more complex model, and we can very, very quickly write the expression for the odds ratio. So that's helpful. So this is sort of something we talked about last time, that getting the confidence interval around this is a very complex expression that involves computing the variance covariance matrix of all these delta terms. And I said last time it would take you a while to do this manually, and so this is what you would look like for a while. And so we need to use the contrast and estimate statements. And so I'm just going to show that on the next slide here. So this is the odds ratio expression for that model that we just saw. It had age, sex, PAMU, and these were sort of these were the beta estimates that came out of SAS. And so, or the beta and delta estimates now that came out of SAS. And so the question is, what's the odds ratio for somebody who's a 40-year-old male with PAMU? You plug in 40, 1, and 1, sort of pieces corresponding to the age, sex, and PAMU, into this formula, and out comes an odds ratio. Well, I'm putting it at the bottom. You would get 8.56. This is annoying. We would rather not have to do this in Excel or manually every time we want to put in different values. And so we use things like the contrast and estimate statements, okay, to sort of automate the plugging in of values for these effect modifiers in order to get the odds ratio that we care about. Okay, because right, we could have just gone to this output back here and said, okay, now I know this formula and I'm going to compute a lot of different odds ratios for sort of things of interest, but this is really annoying. So we use the contrast or estimate statements. You can really use either in logistic. These sort of behave differently in proc GLM or proc mixed or proc gen mod. These are all slightly just annoyingly different between the different SAS procs, so that the syntax is never quite the same. And in logistic, you can use both for an odds ratio. You can't. In other ones, a contrast is special and can only be used for a hypothesis test, but not for an interval. In logistic, you can use both. That's really nice. I tend to like the estimate statement. You don't have to have a preference. I'm weird because I have a preference. But they're generally sort of the same. And the way the syntax for this works is you say estimate, you give it a descriptive label. You don't have to say age 40, sex 1, right? This is sort of you could put anything. You can put hot dogs, you can put whatever you can write whatever you want. This is what you want it to look like in the output. And then what actually is really important are sort of the next pieces. All right, so you in SAS, you're saying, I don't want to have to write out this expression and compute this. Instead, you're going to say prevhosp 1, prevhosp times age 40, prevhosp times sex 1, and then prevhosp times PAMU 1. Why am I doing that? This is basically saying, hey, take the estimate that you have for prevhosp, that beta estimate that you have, and multiply it by 1. That's the 0.0559. Okay, this is the beta that it had for exposure, and you're multiplying it by 1. That's sort of e to the beta part. That's just the beta. And then you're saying, hey, the delta 1 term that you have, or the beta term, SAS just calls it beta, for prevhosp times age, multiply whatever you got, that coefficient, times 40. That's over here. And similarly for sex and for PAMU, those effect modifier terms. Okay, so this is what you're saying. You're saying I don't know what remember, you haven't even run logistic yet. You have absolutely no idea that the value is even 0.4819. You don't even know. You haven't run it yet. You're going to get the output, and then you're going to have it compute whatever it gets times 1, and then times 1 again. And then you need to do this last thing, exp, or estimate equals exp, for whichever one you're doing. That is saying you want not just beta plus 0.001 on the linear scale. You're saying give it exponentiate. You want e to this thing. The formula is not right. The formula is not just this linear piece, but you have to exponentiate it. So you're telling SAS to actually exponentiate this whole thing. Otherwise, it gives it to you on the log odd scale, and that's not useful. So you have to tell it to exponentiate it. And this little CL piece also gives it a confidence interval. Okay, so it's going to give you the wall to 95% confidence interval and the odds ratio. So here it says estimate 8.56. It doesn't call it an odds ratio. It doesn't know that it's an odds ratio. It just knows that this is basically a super generic command for multiply some stuff and then exponentiate it. It doesn't know that it's an odds ratio. So this is just saying, take your estimates, do this calculation, exponentiate in a very user-unfriendly way. Okay, so it's just, but once you sort of get the hang of it, then it's easier. So that's sort of the deal on the estimate and on the contrast statements. So notice you don't have to put age, sex, and PAMU in. The stuff that is essentially times 0, you don't have to leave in there. You could have you actually can write age 0, sex 0, but you don't need to. So again, the EVW sort of approach lets you sort of quickly identify, okay, we're not going to put age, sex, and PAMU in the contrast statement. Only the terms that have prev-hosp, essentially, are going to be in the contrast statement. You need to fit age, sex. The age, sex, and PMU are important. They're being controlled for in the model, but they just don't need to appear in the estimate statement. Okay, so this doesn't mean leave them out of the model. This just means they don't belong in the odds ratio expression. Okay, so that's sort of how we use these to get confidence intervals in this world of EVW models. And of course, right, so the whole point about effect modification, as we've said, is that depending on which values of age, sex, PMU, depending on the values of the effect modifiers, we get different answers for the odds ratio. So here's a situation where we've got 8. Okay, and basically we've got 2 values of sex, right, and then there's sort of the 2 values of PAMU, and then we have it also at different levels of age. So here we have 8 possible odds ratios that you might be interested in. Okay, so this is a male PAMU with age 35. Here's the same person but age 50. And notice you get different odds ratios, okay, and you get different confidence intervals. Some of them are sort of similar. Okay, so this might be overkill. But this is, you can keep putting more and more estimate statements in under different sort of permutations of things that you're of effect modifiers that you're interested in and get different answers. Okay, and this is a lot of information. But you can imagine that, let's say you're writing a paper, you actually could organize this into a piece of, sort of consolidated information that someone could use. So imagine this is your paper, and you said, imagine if there was all this interaction that was actually statistically significant, because I actually don't think it all was in the model. But let's pretend this really was the final model. Then you might make a table that looks something like this, that sort of shows across between people. So there's sort of 3 sort of outer variables here that represent the effect modifiers. And we're showing the exposure-disease relationship in the odds ratio. Let's say in the first column, it's people that had previous antimicrobial drug use, the males, at 2 different values of age, or odds ratio and confidence interval. Then the females. And then sort of the folks that had no antimicrobial use, the males and the females at the age groups. So this is really ugly, but you actually could format it into more digestible information, which I think is nice. You can also make plots of these. At some point soon, I'm going to put online a macro that I've made that actually does a lot of the modeling strategy stuff that we'll be learning. And it actually produces plots of all the odds ratios that let you sort of just quickly present and digest all this stuff. So anyway, so you may need a lot of different calls to, you may have to have a lot of different estimate statements in a row, but you can get a lot of information, and you can even present it in ways that aren't as scary as this table is. So I think that's cool. Okay, so all right, so let's just talk about hypothesis testing for this model, this EVW model, where we had sort of EW terms, we had V terms, we got an exposure term. So the hypothesis testing is not, earlier when we didn't have these interaction terms, we just did a single likelihood ratio test of the exposure. We said that was sort of the thing we cared about. We wanted to see was the exposure significant. When you have EW terms, the hypothesis testing gets a little more complicated here. First of all, we can't just, if this is your starting model, you can't just do a significance test on exposure and say I'm done. Because exposure actually, you can't just test or drop this term, because exposure is also in these interaction effect modifier terms with these W variables. And if you remember, this is sort of like big no-no in regression modeling, that if you have interaction terms, you don't drop the lower order terms. That just essentially creates a very invalid model. And so when we're thinking about sort of testing, doing significance testing, you always address the higher order interaction terms. And what that means really is we test these EW terms first, the EW interaction terms. Okay, and this actually sort of intuitively is how we did stratified analysis. Do you remember, like so you did a stratified analysis in 534. You first do the Breslow-Day test to determine whether there's any effect modification. And then you may have seen some flow charts for this, and it's like, okay, if there's effect modification, then we report odds ratio separately. If not, we do the Mantel-Hansel single odds ratio. You always test effect modification first. Here, one of the reasons you do it is that your model is actually invalid if you did just an exposure hypothesis test first. So one of the things you might do is a global test of any effect modification. You might just say, is there any effect modification of the model? And this might be done with a likelihood ratio test of all the EW terms. Okay. If it's significant, you might say, oh, there's some interaction. Maybe we need to test for some of the terms individually rather than as a global test. If it's not significant, you might decide to drop all the effect modifier terms and sort of proceed. We're going to spend, starting Tuesday, Dr. Kay is going to start sort of going through his modeling strategy series of lectures that really, really goes into this in detail, all the decisions that we make along the way when we sort of decide which variables to keep or drop in the model. So this business of a test of any interaction might look something like this. You might do, like I just said, a likelihood ratio test where the null hypothesis was all three of these delta terms are equal to 0. Okay, it's a chi-square with 3 degrees of freedom because there's three variables that you might be dropping. And so, here we go, let's just put it all up here. Okay, so this right here is the model 1 we had earlier. This is the output for model 1. This was the piece that had the model that had just the V terms and no EW terms. Then you run a second model, right, that has everything, model 3, that has the E's, the V's, and the EW's, and this is its output for the negative 2 log likelihood. Okay, and then we conduct a likelihood ratio test. Okay, in this case, the negative 2 log likelihood only changes by about 2 between the two models. Okay, that's basically on a chi-square degrees of freedom with 3 degrees of freedom, a value of 2 is not significant. It's way on the left. It's in sort of that big hump of the chi-square distribution. All right, so you would say, adding those interaction terms, those effect modifiers, really didn't change anything in the model at all. It added no new information or very little information. Okay, and so you might decide to just drop all of those EW terms, as we just said. Another thing here is that particularly Dr. Kay advocates in his strategy is to do what he calls backwards elimination of the EW terms. And that is that you sort of go one by one through them and make sure that they're all not significant through individual tests. This is very similar to things that were done in EPI 591P, is that what it is, the second semester biostats, where you do sort of, do you guys do backwards and stepwise? And yeah, okay. So this is essentially doing a backwards testing, but just on those interaction terms. So that's one approach. One is, or you can just say, actually, there's no interaction at all. The problem with these global tests in general is that you could have 2 of these 3 are really essentially 0, totally not significant, and 1 might be borderline significant, 0.03 or something, and you test them all together, and you determine that test of all of them together is not significant, even though one of them might be. These are sort of things that happen like 1 out of 1,000 times. Generally, like these are, generally this is probably good enough to pick up any statistical significance in your effect modifier terms. Anyway, so this is what you might do. So again, the EVW model is just a way of sort of quickly identifying, oh, these are the effect modifiers. Okay, so our effect modification test, our equivalent of the Breslow-Day test is a test of the 3 deltas. Okay, rather than saying, okay, that beta 5, 6, and 7, we're just going to say, no, the things I wrote as delta 1, 2, 3 form the basis of my effect modification test. Again, this is just a helpful tool. Okay, so this piece about backwards elimination actually looks something like this. Just as a quick refresher, if we looked at these 3 EW terms, previous hospitalization, times age, times sex, and times PAMU, you essentially drop the least significant thing first. So of the three of these, you see 0.601 is the biggest wall test p-value. Is one way to determine that, which one's significant. Right, and you would drop previous hospitalization times age, and then you rerun the whole model. Okay, and you notice everything changes a little bit, right? That's sort of, this is what I was talking about last time, and I said, what about type 1 versus type 3? And you said, we never learned that. And then I said, okay, it's this idea that like when you have things in the model, everything else is sort of adjusted for it. So if you take something out of the model, you got to rerun it again. Okay, that was this idea. These are all these sort of type 3 tests. So you drop previous hospitalization times age, and everything just sort of dances around a little bit. Okay, because you drop something from the model, you're sort of fitting a different model, and lo and behold, nothing else is significant. It actually could have been that you dropped previous hospitalization times age, and one of these actually became significant, these other EW terms. This happens when you have two variables that are very, very similar to each other. You know, imagine if you had a model, you could actually have a model where like you adjusted for weight and waist size. I don't know. Something which sort of tracks together, and if you put them both in the model at the same time, it's actually possible that neither one would be significant because they're each adjusting for the other. That makes sense? That they're both in the model, weight is controlling for waist size and waist size is controlling for weight, and they're both not significant. And then you drop one, and then bam, the other one becomes very, very statistically significant. Okay, so this is, that's sort of the idea with these p-values, that there's sort of everything's adjusting for everything. Generally, you don't really want to put variables in the model that are too similar anyway. If you put two variables in the model that are super duper similar, you get something called collinearity. And that's actually something we're also going to have a special lecture or two about, collinearity, which is when you really put redundant information in the model and it blows up. And how to know that you've done that isn't always so straightforward. And so we're going to talk about that as well. Anyway, we're talking about dropping previous hospitalization times age. And so we do that, and then we look at our EW terms, and we say, none of these are still significant. The larger p-value belongs to the sex times exposure row, and then we would drop that term, rerun the model, and now the last EW term is not significant either. And so the global test, the global likelihood ratio test of any effect modification returned a non-significant result. That was the 2.0 something. And then we did this backwards elimination, which sort of just validated, yeah, there's really no effect modification here. So that would sort of leave you, once you do that, you're sort of back at what we had as model 2, which had just no effect modifiers in it. Okay, so that's going to sort of wrap up this part of the lecture before we jump into matching. So this was sort of what is the EVW model. We're going to use it more during matching. There's this interesting side thing here. It's a side thing. It's interesting. This is how you trick the computer into doing contrast statements without a contrast statement, if you're interested. And this basically is a way to have you write the model differently such that the e to the beta, e to the beta represents the odds ratio when you have effect modification. So what I mean by that is normally we said that when you have effect modifiers, it's e to the beta plus the sum of the deltas times w's. That's the expression when you have effect modification. But there's a way to reconfigure the data and the model, and that's sort of gone over here and here on these last few slides. There's a way to basically trick the computer into fitting a different model where e to the beta actually is the odds ratio when you have effect modification. This is more annoying to do than a contrast statement, okay? So the reason it's here is like sort of, we've left it in. It's sort of a residual from when we used to have more people in the class who used SPSS. Does anyone here primarily use SPSS? Good. Or not good. Good with respect to the convenience of this course. SPSS is a perfectly respectable package, but it actually has no contrast statements. Every year or two, I keep checking to see whether they add the contrast statement. It has logistic regression modeling, but it doesn't have a way to do custom odds ratios. And so in order to get anything beyond e to the beta, you sort of have to trick it into fitting a different version of the regression model. So that's sort of why we've always had this in here. If you use SAS, this is completely uninteresting, other than it's like a cool thing you could do. This sort of goes into the party tricks category that we talked about last time. At a party where you have a computer. This is a very special party. So we're going to talk today just about the specific application of logistic regression to match data. And this is interesting because not just because match data is a certain type of format to a study that we encounter as epidemiologists, particularly in the case control study, but not exclusively. It's interesting because it has a particular epi purpose, and then it also actually requires a different version of the logistic model called the conditional logistic regression model. Okay, and this is something I know that you saw also in Epi 534 briefly, so it shouldn't be totally new. And we'll just talk about how we're going to revisit that, and we're going to talk about the EVW model again with a matched analysis. So I'm going to sort of not spend too much time on what matching is because you've heard it so many times now. I need to set the stage, so we're going to do that, and then we're not going to harp on all the nuances of matching. And then we're going to talk about how we analyze match data, and again, because you've done this with stratified analysis, we're going to do it quickly, and then just sort of go into the issues of logistic regression with match data, and then just talk about a few other miscellaneous topics in matched analysis. We'll probably finish this on Tuesday, so we'll just get as far as we can. Any questions on the previous stuff? We should just pause and collect before we just jump into this. Any burning questions on the EVW model or contrast statements? Speak now. Okay, we're going to keep just plowing forward with logistic regression, but feel free to raise your hand. I know it's hard. There's 150 people. Raising your hand feels sort of weird, but it's okay. So this is a slide, I think we had it in the first lecture, that just talks about very, very quickly all the things we do as epidemiologists, all the different ways we control for things, okay? And we definitely ran through these with pictures of babies, but this is sort of our toolkit of all the things we cover in our courses and really in our day-to-day work as epidemiologists for controlling for factors, typically in observational studies except for randomization. And we talked about how matching is one way that we achieve balance of confounders between exposed and unexposed groups. And the way we do that is we intentionally arrange groups to be like each other on factors of interest. And when we do that, and the factors of interest are the confounders. And when we do that, we sort of balance the data set on those confounders. So we say, in the case control study, we actually are balancing the diseased and undiseased. And in other forms of match studies, it's the exposed and the unexposed. Remember, the case control study is sort of like a study in reverse, right? You go and you find people with disease and controls, those who don't have disease, and you sort of play things in reverse, and you measure exposures. So the basic idea here is matching is a very intentional process. You say, hey, I got a case, this is their age, this is where they're from. We're going to go find a control that essentially is that age and is where they're from. It's a very intentional process. It's super labor intensive because you actually are really like playing the marionette strings, and you're really determining what your sample is comprised of. That's very different than sort of what we do in stratified analyses on a just totally observational. We did a cross-sectional study. We see who came to the project. We didn't limit people in the project in any way, but we just analyzed the data in a stratified fashion. Matching is a very, very intentional process. Okay, so mathematical modeling is what we're talking about here in this course, right? We could, and as I said on the first day, we can actually combine statistical models with any of these techniques. That's sort of the cool thing. Logistic regression can happen with any of these, can be done in conjunction with any of these above, and then including matched analysis. Okay, so we essentially said this already. Matching is used in many, you can use matching in any of the study designs. It's really introduced to EPI students through case control studies, but really it's done and you can do it in any types of projects. So in experimental studies, this is called blocking. It's mostly, this is a term that is used in the agricultural experimental world, but that's sort of where it's done here. This is sort of where you, yeah, it's okay. We're not going to talk about it. We're not going to talk about agricultural experiments, but we can. My undergrad degree was in this. We can talk about like cows and fields and stuff. It's great. But really, from epidemiologists, we use matching in the cohort and the case control designs, right? So, oops, sorry. In the case control design, it's, again, you're playing time in reverse. You sample your cases and your controls, and you find you find controls that really look sort of like your cases, and so you're matching and to get the confounder distribution between the cases and the controls to be the same. In cohort studies, it's we sort of pair people, we take exposed and we find unexposed that sort of match the exposed folks. So a really good example is something I just mentioned at some point in the past, and that was in a cohort study like that I'm working on with Zika, where we have, it's a cohort study, but households comprised of exposed and unexposed form sort of matched sets. So households are a really convenient way in prospective study of conducting matching, right? So you can sort of doesn't have to be in the case, this sort of reverse case control way. You can imagine all sorts of matched prospective studies as well. So, okay, so what is matching? This is, okay, I'm sort of talking ahead, I'm getting all excited, I'm talking ahead of the slides. What is matching? We all know that this is basically selecting comparison group members that are similar to some index group. This is a super generic way of saying selecting control group members to match disease group folks or exposed and unexposed, right? So, right, depends which study design. In the case control, it's cases to controls, or in the cohort or the prospective designs, it's exposed and unexposed. So I'm going to use these little symbols, by the way. So this is me doing briefcase versus skateboard as a rough proxy for age. You can define the age cutoff. So you can do the age cutoff for skateboard versus briefcase at whatever. Maybe some people might like commute on their skateboard with their briefcase, and I'm not going there. But so, and then you have male, female, and then we have purple and green people. But the basic idea is that you have so here you have a case who's an older female who's purple, and you find a control that looks like them who doesn't have disease. So this is, and if they have a D on their shirt, they're diseased. And if you have an E on your shirt, you're exposed. So that's sort of my idea here, graphically. And so why do we do this? Again, what's sort of the benefit? Is that it's a really great way to balance the confounder distributions between two groups. What's also cool about it, we don't really say that much, is it lets you control for very complex confounders, right? Like, imagine if you had twins or household contacts that you had a diseased person, you match them to the undiseased in their household, or exposed and match them to the unexposed in their household. Not only are you controlling for confounding, but it's a very complex set of things that may be very hard to measure, right? Imagine the questionnaire that you have to administer, and if you weren't doing matching and you wanted to measure what it means to be in a household or measure what it means to be in that family, you may have to collect a ton of data, right, on what does it mean to be in that household. Well, the structure's like this, the plumbing's like that, the air is like this. Whatever it is, it's actually a very, very complex set of things to measure and analytically control for. If you just match on households, you sort of just get that out of the way. They all are in the same house, they're all exposed to the same environment. We've balanced on that complex mix of what it means to be in that household. Same with families. So you can control for complex genetic makeup and all of the emotional baggage of your family, or whatever it is, by matching on the family. And that is actually very powerful and sort of understated. So it actually gives you something above and beyond analytical control for confounding. You sort of just wipe the slate on something complicated. The other thing is, and that's actually related to this idea of variable reduction, right? I didn't have to go measure the 400 attributes that makes your family what it is, and that's why when we measure your PTSD or whatever, it's to your family, whatever that is, where we didn't have to give you 400-page questionnaire or 400-question questionnaire. We got rid of it in one variable, household. And so it's actually a variable reduction technique. It saves you from actually measuring and controlling for a lot of stuff. And the other one is precision. So you actually, in doing all of this, can have a much more precise estimate through a very clean sort of control for household or for match set or so forth. Again, you can get a very precise answer, a narrow confidence interval potentially through a matched analysis. So we generally control for very complex or important confounders through matching. So it's a nice technique. It's not always possible. It's a complicated technique, right? Because when we do matching, we have to find people that are similar. We have to find people, our controls or our unexposed, who are similar to the cases or the exposed. And that actually adds a huge administrative burden onto your project. So and it may actually be really difficult. We can do this through either exact or category matching, which is on the coming slides. Another one is called frequency matching, where you select a group of controls to represent a group of cases. This one's not used as much. We're going to sort of talk more about individual matching today. So what I mean by individual matching is this very, very precise process of you decide in your study that sex, age, and race are important. So here is a female 14-year-old who's green, and is a case. And then we go out into the community and recruit a control who looks demographically like this case. Same for a female who's purple and 33, and then and so forth here. So individual matching is done on an individual basis, and you form very, very, very specific match sets. Okay, that's sort of the idea here, and they have to match exactly on all the features. In practice, we often don't do exact matching. We do something called category or caliper matching. And this is actually where we sort of loosen up a little bit, because finding someone who's exactly that age is often difficult. Sometimes we won't, if you have somebody from a specific, let's say you're matching on geography, which is another common sort of matching factor, again, because geography has wrapped up in it a whole lot of stuff. And if you just match on neighborhood, that's controls for a lot at one time. You may say, well, maybe we will relax what we mean by neighborhood. Maybe it includes the entire zip code, or maybe if it was census tract block, we're going to match on census tract. Or there's sort of ways to relax things in order to increase the chances of you actually finding a match or a control. In actual field work, this is like a whole art. It's just about doing matching well and sort of coming up with the right sampling, sort of getting the right sampling frame essentially together in order to do all this. In practice, what we do is usually called category matching. And again, so here, what's been relaxed is the age. So here we're matching on age bands. We have a control who's in the same age band as the case. And again, this is all fictitious. But basically, it's a huge administrative task to do matching. So the payoff analytically is worth it. But doing a household match study is much more complicated than like nailing a flyer to the tree that says, come to my project, I'll take anybody, right? That's a much more involved process to do a very good sort of household-based project. And so, again, the payoff is huge, but usually there's a much more administrative challenge to it all. Okay, so again, should we match this? I think we've sort of covered some of these pieces here. Again, the decision whether to match is, I think, often really based on the feasibility and logistics of it. You really should only match on, here we go. You should only match on factors that are really important, strong risk factors that you think may also be confounders. So things that are variables that are very influential in the outcome that you care about, things that you think are going to be a big deal. You're not going to match on some extra, small little item that you're not sure is important. And so I think there's just a lot of logistical, logistical pieces to this. And again, you really only want to do something that's going to really be if it's something that's going to be a strong factor, that's a strong confounder, then that's really a big piece of this here. If you only want to match on a strong confounder. The other one that I think maybe we haven't glossed over in some of our courses is that matching factors have to be ascertainable, which is like sort of duh. Everything has to be ascertainable in order to study it. But what I mean by that is some things may actually require consenting and enrolling somebody to know. So there's sort of this like logistical piece to this, right? Like I want to match on your blood type. Well, I may actually have to extract blood from you to know your blood type. In order to do that, I have to enroll you in the project. And so even though it was an important factor, I couldn't match on it until I launched the study, if that makes sense. And so usually when we do matching, it's often on very administrative data, where you live, what your age is, right? And that's just there's sort of again, a lot of this comes down to logistics, is that you really a priori can't match on stuff that you need to consent somebody to get. So again, it's sort of an obvious piece, but something we usually gloss over, and that's sort of another piece to thinking about matching variables. That doesn't mean, sometimes you actually you see matched analyses on a bigger data set where maybe some of those things were measured. So imagine you have access to this blood registry data, a huge database of zillions and zillions of blood donors, and you actually have their blood types because it's a database of blood donors. You can actually set up a matched study by sort of extracting data selectively from that registry. You can say, I'm going to pretend that I'm going to do a matched analysis of 1,000 blood donors, and in that case, you actually are able to recruit the cases and controls or whatever it is based on the blood type, right? So you can always perform a matched analysis inside of some larger data set. What I'm talking about here is really about matching when we think of it as you set up a matched design study. So matching is really sort of broken into two pieces. There's sort of the setting up a study that's a matched study, and then there's really the analysis of data in a matched way. And that second part doesn't necessarily require these logistical considerations. The other piece here, actually one last thing to mention, because it's going to come up in our logistic modeling, is that there is one trade-off to know about all of this, which is that when you match on something, you can't measure its association with either the exposure or the disease. Okay? And this has to do with, let's say you have a case control study. Okay? You match on sex, let's say, and some other factors. Let's just say sex. So we match on one factor. Well, you've exactly balanced the distribution of sex with the cases and the controls, right? You sort of manipulated the distribution between the cases and the controls of sex. And so what happens is when you do this matching, you can't actually assess in your analysis the associations with the factors you matched on. So you sort of like got rid of the factor from the analysis, okay? And so if you were doing a study and you actually also wanted to know the effect of sex in that study, if you matched on sex, you can't. So again, it's about these trade-offs. If you don't care about that, then maybe that's okay. If you also cared about the sex effects in the study, then you shouldn't be matching. So it's a huge, complicated set of decisions for a given project. Okay. So what do we do? How do we analyze data that arise from a matched study? And there's sort of two buckets here. There's stratified analysis and the Mantel-Hansel techniques, where you sort of stratify on all these matched pairs, which I'm sure you've all seen, because we talked about it before. And then the other one is the logistic regression approach. And you can actually fit other regression models to matched data as well. You can do matched linear regression. In fact, right, you've probably seen the paired t-test, right? For paired t-test, that's actually a matched analysis, right? The paired t-test and there's sort of linear regression versions where you have sort of 2 time points or more time points, is really a form of matched analysis where you sort of have 2 observations on the same thing, and you're computing the difference, and that's the paired t-test. So there's a lot of other techniques that you've seen that sort of involve 2 observations on the same thing that are really analyses of matched data. So there's, why don't we just stratify analysis our way out of every match study? So there's some very, very specific reasons. I think the most important one here is that in the stratified analysis, in the Mantel-Hansel methods, if you remember from 534, you only can control for matched factors. So what I mean by that is if you matched on age, sex, and race, and you do the Mantel-Hansel odds ratio, you do that, remember that you make a sort of a funky 2x2 table. We're going to see it coming up. Let's just jump to it. It looks like, hold on, jumped over it. No, it's still coming, sorry. Here it is. This was Mantel-Hansel, right? You remember you make this W, X, Y, Z, and you make, or this is the McNemar table, the McNemar version of the Mantel-Hansel result of the analysis. This is all from 534. Do you guys remember this, right? Okay, good. We're good. So when you set this all up and you do this analysis using the McNemar test or the Mantel-Hansel method, and you do X over Y as the odds ratio, you're controlling for the matching factors because you make all these tables that represent each matched pair, but you can't actually control for anything else. Okay, so what I mean by that is, and I'm going back, I'm sorry, here we are. Okay, let's say you match for age, sex, and race, and you do a McNemar X over Y odds ratio, that's it. That's the only result in your study. You're done. That's sort of it. Okay, you can't control for other things. What if we matched on age, sex, and race, and then we enrolled some people and we made them run, and then we measured their blood pressure, and then we asked them, hey, do you normally run? What was your activity level, or whatever, before we made you run? And then that was your questionnaire. And then you make them hop on a scale. Right? You might actually collect other data of interest that may be potential confounders or effect modifiers or whatever in the rest of the conduct of your study. The Mantel-Hansel, the McNemar approach that we learned last semester actually precludes you from controlling for those in the analysis. And so a logistic regression model lets you simultaneously control for both the matched and the not matched factors. Okay, so that's why we're here. That's why we're talking about this. And so that's really, really important. Okay, that's sort of the innovation here, is that you would be stuck with a very simplistic analysis otherwise. And there's sort of another piece here to just very, very, very quickly. I think this is probably something you covered. Is that if when you do a matched study, you recruit matched pairs. Not only was it an attribute of your design, you put all this money and you did household sample or whatever it is. Not only was it a design attribute, but you have to carry through the whole analysis that way. You can't just give up and say, okay, we got a data set, let's compute statistics on this data set like any other data set. Everything has to be now either that McNemar test or the logistic, sort of the conditional logistic model. You have to carry it through because you'll actually get the wrong answer if you analyze it in a non-matched sort of way. And so in a case control design, you get a biased downward or towards the null, that is odds ratio. And in the cohort study, you get a wider confidence interval. So you actually will get a worse analysis if you don't sort of follow through. These are just a few things to remember. So if you did a match study, analyze it in a matched way. Okay, so then the other one is that sometimes we can sort of aggregate data to get more information in a match study, and that's actually sometimes very helpful. So for example, imagine here's a study, here's two matched pairs from a study. Okay, here we have briefcase carrying purple females. Okay, those individuals make up pair 6, and we also have two such individuals who make up pair 4. Okay, these 2x2 tables represent their exposure and disease data. Okay, so here pair 6 was two women, one was a case, one was a control, and they were both exposed. Pair 4 was two women of the same demographic profile, one case, one control, and the case is unexposed and the control is exposed. If you remember from 534, this sort of makes up the data for matched analyses, right? You have all these pairs where there's only two people in a table, and so this is what those data look like. And what's interesting here is you might say, well, look, pair 4 and pair 6 are sort of comprised of the same people in terms of they're all women of the same age and all of the same race. And so you actually can often pool the data. You could say, let's make a new pair, call it pair 100, and actually put all 4 of them together in the same match set. Okay, so this is just another, this is my slide of miscellaneous things to know about matched analysis. Okay, so this is helpful because what happens is, you might say, well, why didn't I enroll them together to start with? Why did I put them together afterwards? All right, so putting them together afterwards, a table of 4 is going to give you more data than it's going to be a better analysis if you have a table with 4 people than with 2. And what happens is in studies, we only conduct them, if you're doing a prospective study, you're sort of recruiting controls as you get cases. So what if 2 months went by between when you enrolled pair 4 and pair 6? So operationally, when this case came along, you went and found a control. A few months went later, another case comes along and you find another control. Lo and behold, it turns out they actually were demographically the same, and you can actually put them together in the analysis. And that's actually a good thing, because now you have a table with 4 pieces of information rather than a table with 2 pieces of information. Anyway, this is just a small minor point, but again, this is sort of the operational side of matched analysis or matched studies, and then like the real world data side, where you can sort of put these things together. Okay. So I'm going to, again, this is just sort of, again, Matt, this is sort of here. This illustrates what I just said. Here you have sort of different pairs, pair 1, pair 2, pair 3, pair 4, and this is just sort of saying, look, again, if you imagine you enrolled the study only one way in time and you get all these pairs, you really see here that there's really only 2 demographic sort of makeups of these match sets, and you actually can put 1 and 4 together in one sort of matched group, and then you can put 2, 3, 5, and 6 together. And again, doing this sort of gains precision in your analysis. Okay, this is going to be a better analysis if you have 2 big groups rather than six tiny ones. Okay, so it's just a small point, but helpful. So what we're going to see in a moment is that this is not going to work for logistic regression. Okay, just off the shelf if we use the unconditional model. Okay, because what's going to happen is if we did an analysis like this, imagine if you wanted to look at the exposure-disease relationship in a pair-matched study with 100 cases. It's a case control study. Okay, you wanted to sort of, so the technical way to deal with this, if you sort of had 100 matched pairs, each with 2 people, you would have to fit a model with 99 dummy variables, each representing 1 matched pair. Okay, that would sort of be the way to deal with that analysis. That would sort of be the logistic model that corresponds to a 100 matched pair study. This is exactly the same as doing like 100 stratified tables in a Mantel-Hansel test or the McNemar test. This is exactly how you would do that. There's a problem though. This is a ton of variables. This is way too many variables. Not only is it annoying, and it's a ton, it's annoying to write out, and it's annoying to fit in the computer, but it actually, the SAS will blow up. It's not going to I'm sure you've dealt with your share of SAS error messages of varying levels of hieroglyphics, and this one is just going to fail. And the reason it's going to fail is that how many data points do you have in this study? 200. You have 200 people. There's 100 pairs of 2. All right, that's a pair. And so you have a data set with 200 observations, and you're fitting 99 dummy variables, and then it's fitting an intercept and an exposure. You've got 101 terms in this model. It is just not going to be happy. It will not run. Okay, so this is why we need a different approach. So this is really not good. So that we're going to sort of come back to this with a conditional model. And so, there we go. Okay, so this is sort of the idea. I'm just going to very, very quickly go over what the other way, which is the the McNemar approach, just for a moment, right, which is in 534, this is what we did before we did logistic regression, is we would sort of enumerate for the pair-matched situation. Not every matched data set has two people in each pair, in each matched group. But in the pair-matched situation, you sort of enumerate, like, hey, how many tables look like this, where both the case and the control are exposed? You can also enumerate the opposite, where both the case and the control are unexposed, and then sort of the in-betweens. Case is exposed, control is unexposed, and then the opposite of that, where the case is unexposed and the control is exposed. Okay, that's a mouthful. This W and this Z are totally useless in the analysis, right? That was sort of the innovation with the McNemar test, right? The whole idea is that if you see a case and a control, and they're both exposed, that tells you nothing about whether the exposure is related to being a case or not. The exposure is sort of ubiquitous. They both got it. You can't tell. And the same with if you see a matched pair where they're both unexposed. You say, nah, none of them's got the exposure. Can't tell if it's associated. So neither of these really supports any insight. What does support an exposure-disease relationship is when you see a split, right? You say, hey, look, the case has the exposure and the control doesn't have the exposure. That, if you saw that a lot, you would say, that sort of suggests that, that exposure and being a case are related, right? And the opposite situation goes the other way. Look, the controls seem to have the exposure. That's sort of a counter-argument to these guys, the X's, the pairs where you have a case who's exposed and a control who's unexposed. Right? And that is exactly why you have the odds ratio is essentially the tug of war between the X's and the Y's. If you have as many X's as you have Y's, you sort of can't make a decision. You say, I got pairs where the case is exposed and the control isn't just as often as I have the reverse. And so that's sort of the null value of that odds ratio, the McNemar table odds ratio. And then if you have way more of these X's than the Y's, then you say, no, this is a much more common situation where the case is exposed and the control is not. We think that the case, that being exposed has something to do with being a case. So that's sort of the whole motivation for this. It's unfortunate because you often do these matched studies and a lot of the data is in the W and the Z categories, which is sort of depressing because you'll enroll 100 people and then you have only like 10 in the X or Y side here. Then you have 90 pairs where neither is exposed or both are exposed. And those are depressing because sometimes that actually, if it's a rare exposure, that actually could happen, particularly in the Z situation here. But if you're sort of mining for rare exposures in a case control study, you might get a lot of Z's and be very, not sleeping, but be very depressed because you'll have a lot of tables where no one's exposed. So that's sort of the pair match situation. It gets more complicated if you have data with, let's say you enroll, here's a situation where you enrolled 3 controls for every case. Right? Sometimes we don't just do pair matching. In fact, in practice, we often will enroll multiple controls per case. Or you have a household study where you have a single infected or sick person in a household, and then you have everyone who just happens to be in their family enrolled as controls. And so then you get sort of designs that look like this, and then you got more possibilities than just WXYZ. Life's a little more complicated. So I'm just going to jump here to we're going to end on this example in the McNemar situation. We'll start with logistic in the next class. I think this is an example that we've seen before. This is sort of like the archetypical example that everyone uses for matched analysis. It's sort of a very, very common example. And it involves estrogen use in a retirement community, so among women of retirement age. And so this is supplementary hormone use for postmenopausal women. And there was sort of a raft of studies during the 70s and the 80s that proved the association between hormone replacement therapy and a number of different gynecological cancers. And so this one involves endometrial cancer. And so in this study, there's 63 matched sets, and we've got case control status, is really a cancer case or not. and whether the women involved used hormone replacement therapy or not. And there's some matching factors that were of interest. And so here is what the data layout looks like for here. This is actually sort of the opposite of the hypothetical situation I had before. There's an amazing amount of exposure in this group. You have actually 27 of the 63 women on hormone replacement therapy. This was a very, very common practice at the time for postmenopausal women. This is clearly a very, very common exposure. But here is sort of, and then you have only 4 match sets where neither women were on this therapy. So that's actually pretty remarkable, a statement of the state of care at the time. And here we have, again, 29 cases where, situations where the case was exposed and the control wasn't, compared to the opposite 3, where the control was exposed and the exposed was not. So you look at this, you say, wow, look at that. Exposure is really, really associated with being an endometrial cancer case. So that's pretty remarkable. Okay, so again, this is sort of the 2x2 table version of the data, and then you can make the matched version of the same data, which is you arrange those W, X, Y, Zs in a table that looks like this. This is a special 2x2 table where every cell represents 2 people in a pair. This is just the McNemar table that you've seen before. And on this, we have a number of quantities. X over Y is the odds ratio. This is the Mantle-Hansel test statistic and the odds ratio for that. Okay, so again, on this data set, you produce something that looks like this. 29 over 3 is the odds ratio. Wow, that's really big. Is it statistically significant? Yeah. Chi-square test with a test statistic value of 21. So it's very, very tiny p-value. It's way out on the right tail of a chi-square distribution. Okay, so this is sort of the setup. This is the old school 534 setup of things. And then what we're going to do next class is take this further with logistic regression, and we're going to talk about how to do that. So, and then we're going to get through this, and hopefully at the end, we're going to work on modeling strategy with Dr. K.